In this problem, we're given n cards that are face down, and each card either has a number 1 or 2 on it. And what we want to do is we want to correctly guess the value of all the cards, whether each card is a 1 or a 2, right? So in our input, we're given the number of cards, and then m would be the next, and the number of following m lines. So we're given two indices of cards, and we're given some number z. And the only thing that's true is that axi plus byi plus zi is an even number, right? So let's assume xi is 1 and yi is 2. So what that means is that if we look at the card at index 1 and the card at index 2, and we sum those two values together and add that value to some number zi, that number is even, right? So what does that mean? So now this value z, it doesn't really matter what it is. So it would matter if we want to find out what the actual value of each card is, but we just want to find out the number of cards we need to flip over on our own to find out the value of all the cards, right? So let's look at this test case, right? And let's assume, okay, let me change this a bit. So due to some audio issue, I've actually just solved this, but the audio was bad, so I'm just going over the answer again. So let's say it is something along the lines of, we have 3 nodes and we have 2 lines, and 1, 2, 1, 2, 3, right? What are the minimum number of cards we need to flip such that we know the value of every single card? Well, the answer is 1. Why is that? So let's say we have 2, right? So if we just know the value of 2, we now know the value of 1 and the value of 3. Why is that, right? Let's say the value at index 2 is 2, right? 2 plus 1 is 3, right? That implies that this has to be a 1, because 1 plus 3 is even, but 2 plus 3 is not even. And the only values that these cards can have are 1 and 2. Using the same logic, so therefore if this is even, here, this is 2, right? So therefore 2 plus 2 is 4, which means the value of the card at index 3 has to be even as well, because even plus even equals even, whereas even plus odd equals odd, right? So the key thing to know is that this value doesn't really matter, but once we flip the card at index 2, we now know the value of the card at index 1, right? And why is that super useful? So let's say we have some other thing, right? Let me just okay, this doesn't matter, but let's say we have one more line where index 1, the card at index 1 is linked to the card at index 5, and the offset of z is 3, right? So let's say we flip over 2, right? So now that we flipped over 2, so we now know the value of 2, we now know the value of 1, and now we know the value of 3. But now we also know the value of 1, right? So now that we know the value of 1, we now know what the value of 5 is, right? So just by flipping over this 2, we now know all of these answers for 1, 2, and 5. 1, 2, 3, and 5, right? So that's how we solve this. Okay, so since we need to care about which cards are linked to which other cards at which indices and all that stuff, the easiest way to store this information is in a graph. So we first read in n and m, and then in the next m lines, we will read in x and y. So this is the card at index x and the card at index y, and then I zero index everything, and then what you do is you just say they're linked. So by doing this, so this array of vectors here, this is basically the graph, and what you do is by pushing back y at index x and by pushing back x at index y, you're saying, hey, x is linked to y and y is linked to x, and then we just increment the number of times we see x and y. Why is that? So one of the key things to know when solving this problem is that the best way to tackle it is to first start off with the card that is linked to the most number of other cards, right? Because that will lead to the least amount of flips, right? So let's say if this card 1 is linked to 2 and 1 is linked to 3 and 1 is linked to 4, right? But this card 5 is only linked to 4, if we flip 5 first and then flip 1, we need 2 whole flips, right? But since this 1 is linked to the most number of cards, let's flip that first. So now we know the value of the card at index 1, at index 2, at index 3, and index 4. And now since we know the value of the card at index 4, we know this. So we know the value of the card at index 5. So now by flipping the card that's linked to the most number of other cards, we now need less number of flips, because now we only need 1 flip. Because we only need to find out the value at index 1 to know all the other cards here. So that's the key observation to get the lowest number of flips, right? So that's why we need this map. And then what we do is we store the value first and then the key, right? And then I go from back to front. So I would then go from the card that has the most number of connections to the card that goes to the least number of connections, because I go from the end to the start. You could easily go from the start to the end by making this minus, but let's just go from the end to the start. So here, we start at the very last element in the set, which we know for a fact is the one with the most connections, because the set is ordered. Sorry, yeah. And because of that, we go from the end to the start, and then we first check if we have seen this node before. If we have, we move on to the next element. But if we haven't seen it, we're like, okay, we now flip this card over, and then we visit all its neighbors, and all its neighbors, neighbors, and neighbors, 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 and so on and so forth, right? So we run a DFS on this card, right? So we first visit this card, and then we visit its neighbors, neighbors, so on and so forth, right? And by doing so, we now flip a card with the most number of connections. We take off all its connections and all its connections. So then we're just left with a smaller subset. And so that's why so this answer just means we just flip this card, and then this basically tells us what are the indices of cards that we know the values for, right? And so the answer is what we output here, and it works. And just to show you proof, yeah, voila.